This section is about increasing and decreasing functions. The first thing we want to realize is what is the true definition of increasing. If we're looking at an increasing function, we're looking as we go from left to right, when is a function going up? Decreasing means as you go from left to right, when is the function going down? And a constant is when there would be no change in your y value. So, when we determine intervals of increasing and decreasing, what we're also looking at is the slope of the graph. A function is increasing if its slope is positive. A function is decreasing when its slope is negative. Well, as this is a calculus course, we know slope is directly related to the derivative of a graph. The slope is the derivative. So when we said a function is increasing when its slope is positive, what we're really saying is a function is increasing when f prime of x is positive. And a function is decreasing when the derivative f prime of x is less than 0 or negative. Yes. Likewise, we could go the other direction. If the derivative is positive, that means the function is increasing. And if the derivative is negative, that means the function is decreasing. So, if a function is differentiable on an interval, and its derivative is positive in that interval, then we know it's increasing in that interval. If the derivative is negative in that interval, we know it's decreasing in that interval. And if the derivative is equal to 0, we know that it's constant. The rest of this section will be looking at how do we determine when a derivative is positive, how do we determine when it's negative, and how do we determine when the derivative is 0, because that'll answer the big question of when is my function increasing, when is it decreasing, and when is it constant. So now we want to look at when is a function decreasing on an interval, or how is it increasing on an interval. To do that, to determine when a function is decreasing and when a function is increasing, what we really want to do is consider the derivative f prime of x. Using the simple power rule, we know that the derivative of x to the fourth is 4x cubed. So consider that on the interval negative infinity to 0, and then separately on the interval 0 to infinity. Consider the first interval, negative infinity to 0. All of your x values are negative, so when you think about it and you look at 4x cubed, when you plug in any negative number in there, the whole entire thing would be negative. That means on the interval negative infinity to 0, the derivative is negative. And then we know if the derivative is negative, the function is decreasing, which I have now written out. Consider on the interval 0 to infinity. Again, we're looking at 4, plug in any number from 0 to infinity, cubed. When you plug in a positive number cubed is positive, times 4 would still be positive. So what we've said is on the interval 0 to infinity, this function, the derivative of the function, must be positive. Again, if the derivative of the function is positive, then we know the function is increasing. Looking at the next example, they want to show that something was increasing on a given domain. So all we have to do for that one, find the derivative of the function, consider it on the interval, which this interval would be 7 to 12, and show that the derivative must be positive during that interval, which can be shown in the completed notes. So how do we determine when a function is increasing and when a function is decreasing? Again, we said a function is increasing when its derivative is positive. A function is decreasing when its derivative is negative. But consider a point where it changes from increasing to decreasing or from decreasing to increasing. That point right there is a very special point. The value at that point can't be positive, can't be negative. It either has to be a derivative of 0, or it has to be a point where it's undefined in a cusp like this. So we're interested in finding the points of where a function changes from increasing to decreasing, likewise when a function's derivative is changing from positive to negative or negative to positive. This is such an important concept that we give these points a special name called critical numbers. So a critical number is the value c, an x value, where the derivative is equal to 0 or where the derivative is undefined. What's really important to note about this one is that the original function must be defined at that point for it to be a critical number. So make sure it's in the domain of the original function. How are we going to find these critical numbers? First thing you're going to do is set the derivative equal to 0 and or when it's undefined and solve the equation. So again, to find critical numbers, you're going to find the derivative of the function and find where the derivative is equal to 0 or undefined. So the derivative of this function using simple derivative rules would be 2x minus 1. This function is never undefined, which is something we always want to check, but we could set this equation equal to 0 and solve. To solve this, we add 1 to both sides, giving us 2x is equal to 1. Divide both sides by 2, and we have x equals 1/2. Always check to make sure that this x value is in the domain of the original function. In other words, if I plug 1/2 into this function, would it be undefined? In this case, f of x is a simple polynomial function. We could plug 1/2 in, it would still be defined. So this value is defined in the original function. Since it is defined and the derivative is equal to 0, we can go ahead and call this a critical value. X equals 1/2 is a critical value for this function. So, putting all this together, we want to answer our big question of the section, which is when is a function increasing and when is a function decreasing. The way that we're going to do this is use the sign chart method that we learned to determine when a function is positive and when a function is negative back in college algebra. Except remember, we're not trying to find when the function is positive or negative. We're trying to find when the function is increasing or decreasing. And to us in calculus, that translates to when is the derivative positive and when is the derivative negative. So the first thing you need to do is find the derivative of the function and then find its critical values by setting it equal to 0 or undefined. After we've done that, we're going to create a number line and plot these values that we just found. We're going to determine the intervals which we need to test. We're going to test 1 point in each of these intervals, and then from there we can see when is the derivative positive, when is the derivative negative, which tells us when is our function increasing and when is our function decreasing. So let's work through this first example together. We want to find when the function x cubed minus 12x is increasing and when is it decreasing. Again, to us that means when is the derivative of the function positive and when is the derivative of the function negative. So we start off with step 1 of the sign chart method. We want to find f prime of x equal to 0 or undefined. So when I'm looking at this, I look at the derivative first. The derivative using our simple derivative rules would be 3x squared minus 12. Notice that this is never undefined as it is a polynomial function. So the only thing we have left to do is to set it equal to 0 and solve. Setting it equal to 0, I'm going to add 12 to both sides, leaving me with 3x squared equals 12. I'm going to divide both sides by 3, leaving me with x squared equals 4. Take the square root of both sides. Always remember, when you take the square root of a square, you actually have a positive and a negative answer. So I'm getting two answers. X equals -2 and 2. Again, we always need to check these numbers right here in the original function. Think about plugging in -2 and 2 to the original function. The original function is polynomial, so it would be defined. So at that point in time, we can conclude these are our critical values. So next, step 2 is creating a number line, and we're going to mark those CVs, critical values, on that number line. On that number line, we know that the derivative at that point for both of those points were 0, and we want to consider the remaining intervals. The first interval we need to consider is -infinity to -2. The second interval is -2 to 2, and the last interval would be 2 to infinity. We're going to test 1 point in each of those intervals to determine if the derivative is positive or negative in those intervals. That is step 3, creating a sign chart to test our x values into the derivative of the function, which was 3x squared minus 12. I'm going to consider the first interval, negative infinity to negative 2. I pick any x value I want. One of my favorite x values to pick is negative 10 because it's easy to do arithmetic with the number negative 10. If I think about 3 times negative 10 squared minus 12, again, I don't care about the actual number. All I care about is it positive or negative? When I plug in negative 10, I can see that negative 10 squared is positive, times 3 is positive, minus 12 would still be a positive value. So I'm going to go back to my original number line over here, and I know that because that 1 point tested positive, that entire interval has to be positive. We go on and we now pick a number in between negative 2 and 2. Another one of my favorite numbers to plug in is x equals 0 because it's easy to do arithmetic. I'm considering in my mind 3 times 0 squared minus 12. 3 times 0 squared would be 0 minus 12. Again, I don't care about the number. What I care about is that this is a negative value. Because that 1 point was negative, every point on that interval has to be negative. We go to my last interval. The last interval is 2 to infinity. I pick any number that I want, any x value that I want in that interval. I'm going to pick the number 10. I consider 3 times 10 squared minus 12, which would also be a positive value. I go back to my chart, and I note that it has to be positive. That is step 3, completing the sign chart. Now I need to move on to step 4, which is interpreting my solution. To interpret the solution, anywhere the derivative is positive, I know that the original function had to be increasing. Anywhere that the derivative is negative, I know that the function had to be decreasing, and again here is a point where it's positive, so it had to be increasing. So when it asks for when is my function increasing, I just have to look at the intervals that I determined. And when it says when is the function decreasing, I just look at the intervals that I already determined as well. That gives me my final answer, as now shown in the answer blank.